Okay, so next up on our roster is Amir Akbarnejad. At Ames, we're excited to have invited Amir as our student research spotlight talk. Amir is a PhD student at the U of A under the supervision of Dr. Ray from Computing Science and Dr. Gilbert Bigras from the Cross Cancer Institute and Department of Pathology. Please welcome Deep Convolutional Classifiers for Colon Tissue Histopathology Imaging, Amir. Honestly, I'm not sure on this. Would you be able to do it just without it? It's on Google Slides. I think for the sake of time, it's possible. Just continue as it does best. Sure. Yeah, sorry. Sure. Thank you.
Okay, hello everyone. I am Amir Akbarnejad and I am a third year PhD student. I'm so excited to give this presentation today. As you may already know, CNNs are good deep models for image and volumetric data. They are widely used because of matured architectures and availability of algorithms for training and availability of tools and hardware, but not because they are necessarily the best possible choice. Many of you may have already used these models for instance, medical image segmentation or medical image classification. Although they often work very impressively, but they have some issues. The first one is the famous black box issue, meaning that the internal mechanism may not be understandable to humans. Therefore, it is very hard to troubleshoot or improve them. And also they may fail on some instances. And finally, they may not work well on external data sets. For instance, a model which is trained on data from hospital A may not generalize to data from hospital B. And there have been some recent breakthroughs. Of course, there have been many breakthroughs in unboxing these models. And recently, a line of research shows that these models work as follows. They look at training instances, or of course, the instances that they have seen before, and they find some training instances which are similar to the test instance. And based on the found similar training instances, they make a decision for the test instance. And this notion of finding similar training instances is to some degree similar to what pathologists do. There is a prior training in which they see some examples of, for instance, prostate tumors of different grades. And once they look at a tissue under microscope, they notice that the tissue that they're looking at is similar to some grade 3 tumors that they have seen before during their training, and they decide it is a grade 3 tumor. But of course, it is way more complicated than that. It is a simplistic view from my point. And now I am going to show you how a deep classifier solves its tasks by finding similar training instances. And we picked a dataset containing 100K histopathology images from colon tissue images. And there were 9 classes, for instance, adipose and background, cancer-associated stroma, etc. And we trained a ResNet 18, which is a relatively new architecture on 70K of these images as the training set. And the model accuracy reached about 97% on the training set. And here I am going to show you some concrete explanations for the model's decision. Here we see that the test instance is adipose, and also the found similar training images are also adipose. This image, basically, this picture shows us that this test instance has been classified as adipose because the model thinks this image is similar to these images that we are seeing on the right. And besides showing or finding similar training images, we can also highlight to what degree each region contributes to the similarities. For instance, I think I don't have the pointer, but if you pick one pair of these images, you may notice that the model is taking into account the linear structures to detect adipose, which is consistent with the pathologist's viewpoint. And in this case, we see lymphocytes, and both the test instance and of course the found similar training images are lymphocytes. To pathologists, they are well-defined nuclei which are homogeneously scattered. And like before, the first row is telling us that the test image is classified as lymphocyte because the model thinks this image is similar to the 10 training images that we are seeing on the left and the model has seen during its training. And if you look at the heat maps, for instance, in this case, we see that the heat maps are more or less white everywhere, meaning that different regions have contributed more or less uniformly to the similarities, and it is consistent with pathologist's viewpoint. I mean the notion of homogeneity. And before moving on, among the classes, distinguishing between two of these classes, namely a smooth muscle and cancer-associated stroma, is challenging even for expert pathologists. According to this confusion matrix, we noticed that the model has done a very good job in distinguishing between these two classes, and I'm going to show you some example explanations for images from these classes. In this case, the test instance is a cancer-associated stroma, and so are the found similar training images. If you look at the heat maps, you may notice that the model has, to some degree, taken into account the pinky stroma, but it has, you may notice that it has mainly targeted the nuclei. And because another line of research that we are doing also shows this, when it comes to nuclei analysis and I don't know, any cytology related tasks, a machine can perform very well and even better than human eyeball. And in this case, we see the test instance is colorectal adenocarcinoma epithelium. And of course, like before, the first row shows us that this test image is classified as colorectal adenocarcinoma epithelium because the model thinks this image is similar to these 10 images on the right that it has seen during its training. And according to the heat maps, you may notice that to solve basically the regions that contribute the most to the similarities are malignant epithelial cells. And this is completely consistent with pathologist's viewpoint. And here we see an example for which the model has failed. And the test image is a colorectal adenocarcinoma epithelium, which is misclassified as normal colon mucosa. And of course, the first row, like before, shows us that this is classified like this because the model thinks the test image is similar to the 10 images that we are seeing on the right. According to the heat maps, it seems that to solve the task, the model takes into account some regions which are right next to glands. If we look back to the test instance, I mean the image which is shown in column 1, you may notice three white spots, which to some degree look like glands, and it seems that those three white spots have misled the model. And this case, this is another case on which the model has failed. In this case, the test image is a smooth muscle, but it is misclassified as debris. And like before, the first row shows that this test instance is classified as debris because the model thinks it is similar to the 10 images that we are seeing on the right and the model has seen during its training. And if you look at the first column and images 1, 2, 3, and 4, and 5, and 6, the images at row 1 and columns 2 to 6, you may notice some Swiss cheese-like white spots, which are also present in the test instance. And it seems that those white spots or white artifacts have misled the model. And if you want to see more interesting results, you can refer to our paper, which is called JPEGs. And it is actually an open source tool. We have made it public, and you can use it to interpret your deep models and get such explanations that we just got here. And here are my references. And thanks for your attention. Please feel free to ask questions.
All right. We do have 4 minutes for questions. Thank you very much for your talk. So please go ahead and, as before, use the microphone in the center for in-person and use the chat for online attendees.
So I have a question about the images you showed were like small squares of the slide. And normally you have this huge amount of tissue to look through. So can you say apply that, take random sampling of squares for the slide and apply that and then take the consensus rather than diagnosing like individual squares?
Oh yeah. Thanks for your great question. Of course, the diagnosis as pathologists and also are based on the whole slide images, but we use the Gaussian processes to explain the ANNs, which are I can tell you that which are one of the few reliable ways to explain that, and that works only for a model that takes in one input and produces one output. But for whole slide images, because you may notice that there are other techniques, for instance, there is a feature aggregation, etc. We have not done that, but we are going to do that here. Yeah. No problem. Thanks for great question.
Okay. Last call for some questions. All right, we come down, going once, going twice. All right. Well, thank you very much, Amir, for that presentation. It's great to see the class.
Okay, thanks very much. Thank you very much.